Classical free electron theory has long been a foundation in understanding the electrical and thermal properties of metals. Initially proposed in the early 20th century, it presents a model where electrons in metals are treated as free particles, akin to gas molecules in a container. This framework allows for the explanation of conductivity, but as we delve deeper into its implications, several inconsistencies arise, leading to its eventual decline as a comprehensive theory. One pivotal issue with classical free electron theory is its inability to explain the specific heat of metals accurately. According to the theory, the heat capacity should depend solely on the number of electrons. However, experimental results revealed that the specific heat of metals scales differently at low temperatures, suggesting that other factors influence their thermal behavior. The classical model also falls short in predicting the thermal conductivity of metals at varying temperatures. It does not account for the interaction between electrons and lattice vibrations, known as phonons, which play a crucial role in energy transfer. Furthermore, the classical approach fails to address the electrical conductivity of materials under the influence of magnetic fields. This phenomenon, known as the Hall effect, demonstrates that charge carriers exhibit a transverse voltage when subjected to a magnetic field. In classical theory, this is difficult to rationalize, as it does not incorporate any quantum mechanical principles that govern the behavior of particles at such scales. The discrepancies between observed phenomena and theoretical predictions raised questions about the validity of the classical model. Another limitation is its inability to explain the phenomenon of superconductivity, where certain materials conduct electricity without resistance below a critical temperature. The classical free electron theory cannot accommodate the quantum mechanical effects that arise in superconductors, ultimately necessitating a more robust framework to articulate these behaviors. This leads us to the development of quantum mechanics and the subsequent introduction of the Drude model, which sought to reconcile these inconsistencies by incorporating aspects of wave-particle duality. As quantum mechanics emerged in the mid-20th century, physicists began to realize that electrons cannot be treated purely as classical particles. Instead, they must be understood as wave functions described by probability amplitudes. This shift allowed for a more comprehensive understanding of electron interactions within materials, leading to the formulation of band theory. Band theory posits that electrons exist in energy bands rather than discrete orbits, which better explains electrical and thermal conductivity in solids. With the advent of band theory, the concept of conduction electrons was refined to consider electron mobility and effective mass in different materials. This model addresses the discrepancies noted in classical theory by incorporating the crystal lattice structure's effects. In a metal, electrons in the conduction band can move freely, while those in the valence band remain bound to their atoms. The interaction between these bands accounts for the conductivity variations observed in different substances. Additionally, advancements in materials science have revealed that electron behavior is also significantly influenced by defects and impurities within a metallic lattice. Understanding these elements is essential for improving the performance of materials in various applications, including electronics and superconductors. The classical theory did not account for these critical aspects, further emphasizing its limitations. In summary, while classical free electron theory provided a foundational understanding for early electrical conductance, its failure to explain key phenomena in metals led to its decline. The emergence of quantum mechanics and band theory offered a more complete picture of electron behaviors and interactions. These advancements have not only explained the challenges faced by classical theory but have also opened new avenues for technological advancements in diverse fields, including nanotechnology and semiconductor physics. Today, we stand on the shoulders of these developments, equipped with a far more sophisticated understanding of materials that continues to evolve as research progresses. Understanding the intricacies of electron behavior remains pivotal in harnessing materials for innovative applications, shaping the future of technology and science.